Good morning, YouTubers. Today we're gonna be discussing, like for example, what's gonna happen with a free fall, let's say of a baseball like this, and that is kind of, let it go from a certain elevation, and this is the direction, what we call Y direction, and the only force on the ball is like the force of gravity, which is defined as mg, the mass of the ball times the acceleration, and for this case g is basically, I just write it here, is equal to 9.81 meters per second square. If this is the only force involved as this ball falls down, that's what we call kind of a free fall situation. Free fall. If that's the case and that's the only force, remember there's air here, right? Air all over. But we are assuming that the air will not impact the ball, so that means it's called free fall. In that case, if we apply Newton's law that the net force equal, and this is a vector, the mass times acceleration, then we can convert that equation basically to say, whoops, something missing here, to say that the net force F is equal to the mass. Acceleration is basically the change of velocity by time. So you end up with this equation here. Now, the interesting thing that you can certainly do is that force, basically if we continue here, the net force, because basically that's right here, net force apply to this object, and that net force will be equal to m times the change of velocity, and this basically becomes what we call an ordinary differential equation. Ordinary differential equation. And basically if we apply what is the net force, and we assume that it's going to be positive going down, right? In that case the net force basically is positive mg. There is nothing holding down the free fall. That means that mg must be equal m times the change of velocity divided by by the rate of time, and that basically the m cancel out, and you end up with this differential equation that says that the speed of the change in velocity will be equal to the acceleration of the earth. That's called 9.81 meters per second square. And basically if there's nothing that maintain the ball, that hold the ball as it's coming down, then you end up seeing that the m is not anywhere, it's independent of mass. So you can have a big object like this and a small object like this, and both will fall down at the same speed. And that's basically due to this equation here, that we know that as we allow an object to fall down, definitely the speed will be cut off by the drag force, in this case by the resistance of the air to that speed. Now to solve this is straightforward, and you just multiply, separate variables. So t will be at one side and the speed would be another side, so you multiply by delta t both sides. This cancel out, and you end up that the rate of change in velocity will be equal g dt. We want a function, basically for this we want a function that said v as a function of t is equal to some function of t. That's what we want. So in that case, oops, sorry, here is dv. There we go. dv equal g dt. In order to get this, then you integrate both sides. Since g is a constant, it can stay out of the integral. Now at time equals 0, what is the velocity of the ball? In this case, if you are opening your hand and allowing the ball to fall, then at time 0 the speed of the ball will be 0. Now if you threw the ball, that's another, that would at time 0 the speed would be different, would be a number here. Now at a given t for a given velocity, this integral is basically v, right, evaluated between 0 and v. That would be b minus 0 equal v. Now the right side will be, this integral will be gt evaluated between 0 and t. Obviously this right side will be gt minus 0 will be gt. So what we end up saying is that the velocity as a function of t is g times t. Oh, sorry, g, well, let's put this g times t, look better like this. And that's the equation that we have for the ball falling in free fall. So do you end up with an, if I do a graph of this, v times t versus t, at t equals 0, the velocity is 0, but then you have an increase in velocity, which basically is the slope, which is going to be g. That's the slope of this equation, and what it says is that the velocity will keep increasing as time goes by, then as shown here. So that's okay. I mean, this is kind of a first trial that we are saying is that any object in free fall will accelerate at the acceleration of the rate constant of the in this case g, the gravity force, the gravity acceleration, which is in this case g equal 9.81. No problem, free fall, straightforward for the velocity. Now what's going to happen on the other hand if we have the same case, a ball falling down, but now I add another force, right? This force here is gravity, which is m times g, but this force here is force of drag. We're gonna define drag force in a second, but now we have two forces. Remember, we are always in this analysis. Basically, we are working on this. If I were, let me put this way, like you are working on an XY axis. So basically the free fall is coming down, so I'm only concerned with the Y axis, and what I'm saying is that at t equals 0, the ball speed, basically you're letting go the ball, so that means that at t equals 0 the velocity of the ball is 0, right? Now if I apply Newton's law says that force, the net force, always is equal ma, but the acceleration is the change of velocity with respect to time. So now if I substitute what is F here, F, the net force, is, and assuming that going down is positive, in this direction, that means mg minus the force of drag equal m times the change in velocity with respect to time. Here we go. What we need now is the definition for the drag force. Basically that's straightforward. The force of drag is 1/2 times the density of air times the coefficient of drag, which is a dimensionless number, times the area, what we call frontal area, times the velocity square of the object. If we substitute that here, we end up with mg minus 1/2 rho of air times the coefficient of drag times the frontal area times the speed square equal m times the change of v with respect to time. That's perfect. What we're gonna do now is let's divide by m, everybody. So if we do that, we end up with g minus, here we go, all this term here is basically a property of the object falling down, like coefficient of drag, the frontal area, and its mass. You see, those belong to the object. So now if you have something, a big object versus small object, different, this parameter here will be different for a large object versus a small object. The frontal area will be larger for this one and small for this one. Probably the mass for this one would be higher and this will be smaller, and so forth. So there's some changes in this property. I want to call that property phi for, just to avoid rewriting everything. So you end up with this equation. I like to put this more like a differential equation like this: dv dt equal g minus phi b squared. B is 2 squared. So this is a differential equation, but now this consider obviously the gravity, but also consider drag force, the resistance of air. If that's the case, we want to apply, we definitely at the end we want something like this: v as a function of time. That's what we want. A simple equation that we plug time and it provides the velocity. To do that, let's do what we did at the beginning. Let's multiply by dt both sides. If we do that, this cancel out and we end up with dv equal g minus phi b squared dt. Now here we haven't separated variable yet because I still have v, or the velocity, at this right size, and I have time here, but it's straightforward. You divide now by g minus phi over b squared in both sides. You end up a very straightforward equation that says this chain of velocity g minus phi b squared equal dt. Now what we need to do to get what we want, which is obviously, remember, b as a function of time equal a function of time here, then is to integrate both sides. Now how are we going to do this integration? At time 0, what would be the velocity? I'm going to write 0 for now. Could be any value here for a v for a time t. Alright, now the right side is straightforward, no big deal. That integral there is the integral of dt is t evaluated between 0 and t. That means that this integral is t. So whatever I do, my left side must be equal time. That's it. So I only need to integrate this part here to get this, going. Now, how are we going to integrate this? Well, we definitely can use an integral table and compare what we have here to how can we organize this. And there's one particular integral that you can certainly use to do this, but there's something here very interesting, which is that denominator g minus phi b squared can be broken in two parts. Like, you can factor this out, and that's the important thing. Can it be factored? If it can be factored, you are definitely in the right place. If it cannot be factored, then you are probably in the inverse for the tangent. But this one smell like logarithm somewhere because it can be factored. What that means is, like, for example, let's make life easier. Let's work that out. So for example, let's get that integral from 0 to b dv g minus phi b squared. I don't like the way it is right now, so let's divide this denominator by minus phi. If you do that, let's multiply by phi, or 1 over phi, negative as well. So this and this will cancel out, because when you multiply, like for example, by this phi here, will cancel out with this one, and you haven't changed anything. But doing so will make this equation more easy to deal with, in the fact that it will look more like this. You divide by minus phi, this end up being b squared here, but then you move this g over phi down here. Perfect. And remember, all that is equal t. Now, what we need to do is to break these or to factor this. Now that's straightforward because that's you can factor that as you remember. Let's do it this x minus a square as a comparison. That would be x plus a, x minus a. If you compare these to these, the only thing that you need to remember is that a square is basically g over phi. That means that a is the square root of g over phi. If I do that, then basically this is the same as saying v plus g over phi time v minus g over phi, square root of that. And we have factored this polynomial in these two parts. That makes life easier because if I do my integral back and I substitute this part here, we end up with 1 negative over phi times the integral of dv. That would be b plus g over phi v minus g over phi. Alright, and you end up with that equal t. Now this integral here, you can do partial fraction. It would be straightforward to do partial fraction on this, and although you can use the integration table. Like for example, there's a nice integral that says something like this: x plus a, x plus b, which is pretty much identical to this, and this is coming from a table, an integral table. It says that the result of here is b minus a times the logarithm of x plus a, x plus b, and that's it, plus an integral constant depending on whether you have limit or not. All right, so we can apply all this definition here, which is what I want to do, to this equation here. Either that or you can use partial fraction. I'm not going to demonstrate partial fraction now yet, but I'm going to use this the way it is because it's the definition, easy to use. And so if I do that, then what I need to do is basically identify what is a and what is b, which is straightforward. For this case, a is equal, this part here is the square root of g over phi. And what is b? Funny, b is the negative of the same value, g over phi. Remember that this is true if b is totally different, it's not equal to a, because if they were the same, then you would be divided by 0, and that would be not good. So they're different, and that's good. So by applying this rule, this integral rule to this, we end up with this 1 over phi, and here we go. Now remember, 1 over b minus a is this part here, so that's 1 over, easy here. What is a and what is b? B is a negative g over phi minus a, which is g over phi, the square root, and that times the logarithm of whatever is x. In this case, x is v, and a, I said that is plus the square root of g over phi over, and here it says, on my case, x plus b, so that would be b minus g over phi. All right, now remember, this integral, it has to be evaluated between, let's put the limit here, between 0 and v. So that means that this integral here has to be evaluated between 0 and v as the velocity. Now let's work out the details of this side. First of all, let's put a parenthesis here to help to clarify what I'm doing, and I'm gonna work on this in a second. Let's work on this part here. So that end up being negative 1 over phi. Easy on this part here, just same base, you add it up, so that means 1. Now there's a negative coming from here. Negative will cancel out with that negative, so you end up positive, but that's really gonna be 2 times g over phi, the square root. That's perfect. Time the log of v plus g over phi, v minus g over phi. All right, evaluated between 0 and b. That's good. Now, how about this phi and this phi here? Well, this phi here is 2 over 2, right? I can make this easier by saying that this is 2 over 2. And if I do that, because 2 over 2 is 1, obviously phi to the 1. But then this is phi is to the 1/2. So this phi will end up here 1/2. So 2 over 2 minus 1/2 is 1/2. So you end up with this phi 1/2. So this eventually is going to be phi, square root of phi. These two, I can take it out here, and then you end up with this g here, times the log of all that, evaluated between 0 and b. Now, it's interesting, both are the same, the square root, so that simplified to 1 over 2 phi times g. Remember, phi is a parameter that has to do with drag force, and g is gravitational acceleration, so that g will stay 9.81, no big deal. Now, logarithm, let's start to work on this now. V plus g over phi, v minus g over phi, up to there. So now, let's work this detail. This end up being a common factor for that, so let's break a big parenthesis here and let's work that out. So that would be log of, when it's v, is v plus g over phi divided v minus g over phi, no big deal here, easy now, minus logarithm of, when v is 0, we end up with very interesting result here. We want to be careful with that. Negative g over phi. So we close this bracket with this one. Now the result is kind of a weird, and let's keep writing that here, 2 over phi times g. Now logarithm, the first part I don't see any problem. But the second part, this is identical to this, so, but there's a negative. You end up with this. Logarithm of 1, and you will jump from your chair right now and will say that cannot be done. Well, yes, but there's a logarithm here. I mean, you don't take logarithm of an apple. There's always, this is kind of a physics problem, a real problem. So this first logarithm here has to do with this logarithm in this part here. So you need to combine them, and you remember obviously from your algebra courses, like for example, you got something like this, logarithm of b minus logarithm of a, that eventually will be logarithm of b divided by a. The same result. So you apply the same rule here, and when you apply that rule, you end up like this: 2 phi g times the logarithm of b plus this divided by b minus phi g. But here's the catch: that minus 1 end up being, by having a minus 1 here, you want to see it like that. Alright, so what that will do is you end up with v plus, no problem in the numerator, but the denominator -1, this is going to be positive, minus v. And perfect. If you remember all this is the integral part, well, it took a while, of this, everything here, and that should be t. So in other words, I end up that all this perfectly is equal t. But there's an issue here that comes from the denominator. It clearly says that this here must be, at the, at a given point must be larger than 0. It has to be positive, but larger than 0, because if it's 0, we are in trouble. So meaning that v, there's a limit that if we resolve all v, end up being g over phi. Interesting, because this result, or this limiting result, is what we call terminal velocity. So I have an expectation that if I plot the velocity versus time, and the velocity start here at time equals 0, the velocity was 0, this will go like this, and eventually will hit that terminal velocity. Very different when there's no drag and the acceleration is always going up like this. Clearly no drag situation, this one, but this one is with drag, so you end up with a limiting velocity. Now, one issue here, my equation here end up not the way I wanted, because basically it end up like, if you want to plot v over t, and the velocity versus time, you would like that this be like this, time versus velocity. So the way you end up here, it's not that cool, because it's the other way around. It's velocity like being the independent variable at time the dependent variable, and that we don't like it that way. So let's do this. Let's copy this for 1 second. All right, so there's my equation there. Oops. So there we go. We want to have this equation, we want to work it out, end up like this. We want always, since day one we want the equation to look like this. So in term of a function, so that I can plug the time and get the velocity of the object. To do that, let's work this out. So if I multiply by this factor here, the denominator, I end up having something like this: t, the time, times 2 times phi times g, equal the log of all this. I don't want to rewrite all that again, but you get the idea. So if I get to eliminate this log, basically, how about if I get the whole thing to the to the e, and when you do that, then you end up e2 phi times g times time equal, now here, this is the interesting part, you eliminate the log. That means that you end up with whatever is this content here. So that's going to be b plus phi over g divided by phi over g minus v, up to there. Now the only thing that I need to do is to get my equation in terms of v. That would be easy. Let's call this, it's just a constant. That's not a constant, it's a function of time, but let's call it for now is psi. Psi is obviously a function of time, right? So, but just to avoid writing too much, let's call it like psi for now, equal v plus there. If I multiply by this denominator, both sides, I end up with this. up to there, perfect. Now if I apply all these, it says now if I solve for v, I can get this down here and this go back here. That will end up being a, I can, let's do this so everybody follow. Oops, let me stay here. G over phi equal, this go positive this way, the distributive phi or psi minus 1 equal v as a factor psi plus 1, and we end up that the velocity in terms of time equal terminal velocity, the square root of that, so that would be psi minus 1 divide all that by psi plus 1. Very straightforward. Now we recover what was psi, and we said that the velocity of any object falling in the presence of a resistance will be this equation here, which it would be e to square root of phi times g t, that's psi minus 1 over e to phi g t plus 1. And here, my fellow people, is our equation that we were looking that we can easily plot now for whatever property of the object, which is come from, remember that in this case phi is nothing else. You remember that 1/2 the coefficient of in this case the air density, by the way, if you don't know that, it's about 1.25 kilograms per meter cube, times the coefficient of air times the coefficient of drag times the frontal area of the object divided by the mass of the object. And that's basically what I was saying. That was more like a constant, that's a constant. If you know the constant, for example, for a baseball, if I remember the numbers, like for example the coefficient of drag, I can approximate as 0.5. The diameter of the ball is about 7.3 centimeters or about 0.073 meters. The mass is about 0.145 kilograms. And if you substitute all that, remember that the area, the frontal area, is about pi times this diameter square over 4. And if I remember calculating that before, somewhere if it was about 0.00902, something like that. It has unit, but I don't care at this point. But that's a value based on these parameters, and that would be, now it would be straightforward because you know that parameter, you know g, and now you can get your plot of, in this case, of time versus velocity. It's interesting. You can check how this equation behave, and remember this equation comes from an ordinary differential equation. It means that it needs to prove two things. First, the initial condition, that at the initial condition at time 0, this equation must be 0. And it is, because basically you substitute t equals 0 here, that would be e to the 0, that's 1. 1 minus 1 is 0, so everything's gone. So definitely it proves the fact that at time 0, the velocity of the ball falling is 0. Yeah, perfect. Now, at infinite time, when t go to infinite, that means that as t get large and large, this minus 1 or this plus 1 would not, nobody cares about them anymore. So this divided by this, two huge number that will approach to 1, and definitely the approach finally will be that the ball final speed will come to a limit, which called terminal velocity, which is basically come from this ratio between g divided by phi, the square root of that, and that's the terminal velocity, and you can easily demonstrate that. Again, this equation is from the fact that when I did the integration, you remember, just don't fall asleep here. When I did the integration, a little bit more here, the integration was done at 0. The initial condition was 0. If you change this to another parameter, like, I don't know, like you threw the ball at 10 meters per second, then this will be the speed here, 10 meters per second, and you can redo that. Basically would that be boils down to substitute whatever number you have here, and that would provide the correct initial condition. So anything else here that I want to say about it? One final thing is that yes, this solves for the velocity in function of time. How about the distance? I mean, what you really mean, professor, for that? Well, the distance is, I want to know what is the distance covered as a function of time. And to do that, that would be the kind of the second part of this video, because that will require me to integrate this. Because velocity, this definition here, let me copy this. There we go, nice. What is this? Well, the velocity is nothing else than the chain of distance, or the rate of change of distance with time equal, there we go. So we need to separate variables. That would be straightforward, because basically it's only in function of t, so meaning that if I multiply by dt both sides, dy equal, let's fix this a little bit more, so let's delete what is not required here. Alright, time dt, there we go. At 0, this integral is 0 for whatever y for whatever time. So what we need to do is to integrate this. We're going to leave that for another class, and that will provide me how far, I mean, the ball will travel as a function of time, because remember, you are throwing the ball, at a given distance from the floor. Let's say that this is the floor, and you are at a given distance here, y. So there's always this kind of question: what will be the distance covered by the ball? But since velocity is changing as a function of time, then you need to integrate that velocity in order to get then the distance. When the problem ends, like for example, let's say that you threw the ball from a 200 meter height, from 200 meter, so the ball, this problem here is going to be 200, and the question is, what will be the time? How long it will take the ball, t, and that would be the question that you want to answer. If a ball is through at 200 meter and it's a fall with air resistance, how long it takes to hit the floor? That's always kind of the question that we are looking at here. So you always know this side, but this side is a little bit tricky, because we will need to solve after all this is done, this integration is done, then we need to solve for t. All right, and because this side is well known, it's 0, this is 200, so this side is basically the right side, I mean the left side, is going to be the integration of dy is y evaluated between 0 and 200, and obviously this is 200, so 200 must be equal to this And just to get that, then this is the variable that we need to solve finally for t. Again, that will be another video. Thank you for watching. Have a great day. Bye.